make it. A reminder from that I announced yesterday that we'll have a dinner tonight at 7:30. The details will be sent via email to you later today.
Have you said that they don't have to pay?
Yeah, except for drinks. Yeah. Yeah.
I'm not sure.
Yeah, you'll get the details. All right, so Sebastian will continue on lecturing us on scattering theory.
Indeed. Good morning, everyone. So I've realized that the lectures from the 2 previous days were posted on YouTube, and I made a mistake and watched them. There's no quicker way for a person to become a saint than to watch their lectures, because it's the most humiliating experience there can be. But I realized I'm talking extremely slowly during those lectures, so I will try to speed up. That's point number 1. Point number 2, let's review what we talked about yesterday. I need a better chalk. This one is good. Okay. So, the previous episode involved causal transforms and their link to analyticity. So we talked about this example in classical mechanics a little bit. Started talking about an example in non-relativistic quantum mechanics, this spherical well, and we identified certain properties, analytic properties of the scattering amplitudes, like the square root singularity in energy variable. So this is our branch point singularity. We also saw poles, so things that behave like this. They diverge at certain energy E naught, and the poles corresponded depending on where they were found in the complex plane, either to virtual, bound, or resonant states. Now, there's this tricky situation with resonances, because due to this branch point singularity, I told you that the function, complex function that is a scattering amplitude, is defined really on 2 complex planes, not just 1 complex plane, and the real scattering amplitude, what we sort of measure experimentally, I mean, we really measure cross sections, so amplitude squared plus or times some factors, is the boundary value of this analytic function on the real axis, or really there is this prescription of approaching the real axis from above. So remember, we had a cat. This will be the momentum plane. We had a cat. We had some bound states here. We had some virtual states here, potentially. And we had some resonances living in the complex plane and their complex conjugates. So the claim was that there are these 2. So there's 1 complex plane. Let's call it number 1. And there's another complex plane. Sorry. These 2 complex planes in the momentum variable are really the upper half and the lower half, and then they become 2 complex planes if we consider energy variable. So if we perform transformation from P to energy variable, we have two copies of a complex plane. And then, oh yes, so I messed up. There's no branch cut here, of course. So these two complex planes that manifest as two halves in the momentum plane, they are sort of smoothly connected. And yeah, the branch cut appears when you sort of fold them, and the bound states appear here. The function is analytic in the upper half plane, analytic in the lower half plane, and this branch cut is also on the second sheet, second Riemann sheet, or the second complex plane, and there we can have resonances that appear here and virtual states that appear here. Okay, so there were some questions after the lectures. How should we understand these two complex planes? This is complicated. We haven't seen that before. So maybe I should actually have asked, who is familiar with the concept of Riemann sheets? Please raise your hands. As a problem, I took off my glasses, so I don't know who raised their hands. Anyway, I have a feeling that not too many of you. Maybe I should. Okay, so I'll show you a picture on Friday during the colloquium to visualize it better. But one way to think about it is essentially you have a function that has a discontinuity across the real axis. So if you move from this point on the complex plane to that point in the complex plane, you'll just see a jump in the value of the function. So as you move along this complex curve, you will see a function that behaves something like that. So this is some real parameter that parameters your curve. Well, let's say it behaves something like that, then there's a jump, and then it behaves something like that. So there's discontinuity. Now, I claim that these two Riemann sheets are connected one to another, or glued together through this cut. What I mean exactly is that the value of the function in the lower half plane of the second complex plane is an analytic continuation of the function defined in the upper half plane, meaning that if we take a curve that goes like this and continues here, we will see no discontinuity. So we will, if we move across this curve, we will see some smooth behavior, more or less. Now, if we keep going from this point and try to hit the discontinuity again, there are two options what we can do. We can try to land on the first, or so on the second sheet again, and then, again, imagining this is some real parameter parameterizing our motion across the curve, we will see the discontinuity of some sort. So this is how the function behaves, let's say imaginary part of the scattering amplitude behaves when we move following this curve. But we can define analytic continuation in a way. I'm running out of colors. Okay, so let me use the yellow one again. But if we continue this motion and then dive under the cut, we will emerge on the first sheet, which is analytic continuation of the value of the function or the function on the second sheet. So essentially, we'll go here and we will see smooth behavior because we landed on the first sheet, which is here. Not sure if this is intuitive enough, so I'll give you another picture. Instead of thinking, probably from complex analysis course, you know you can think of complex plane as a sphere through a stereographic mapping. So complex plane can be considered a sphere. You can sort of, with some pinching, depending on if you consider infinity in your complex plane or not. Now, you can, of course, imagine sort of squeezing half of the sphere into upper hemisphere. So like squeezing whatever here, there, some continuous way, to make room for second complex plane. So imagine you have two complex planes, and each one of them is a hemisphere. There's a branch point, a singularity in your function defined on the sphere, but motion from one sheet to another is nothing else but just going from a northern hemisphere to the southern hemisphere. So there is that's what this continuity, this analytic continuation means when I jump from one sheet to another, or how it can be imagined, at least. Okay, so I just found out there was this paper published on, or uploaded on archive this night, and I'm not showing this paper to you because it's revolutionary or anything, although judging from the authors, who are very respected physicists, I think it's probably very good. I didn't have time to read it in detail, but I'm showing it to you just to, so you see it's October 22nd, just to point out that you can now go to real world and read papers. What do I mean? If you look at the abstract, you'll start seeing a lot of familiar words that I mentioned yesterday. So, a bound state, you have some reaction, E plus E minus. They mention effective field theory framework, so what Andreas is explaining to you. They mention one of the experiments that I also talked briefly about. But then in the last part of this abstract, they say, well, if you go above the proton-antiproton threshold, there is a pole on the unphysical Riemann sheet. So this is this second complex plane that I introduced further away from the threshold. Then they say, I think there was something else here about the poles. Okay, I don't see it immediately, but you start seeing familiar expressions, bound state poles, complex Riemann sheets, etc. So if you go and read this paper in more detail, you will see that what they're trying to do is essentially use concepts from S-matrix theory to constrain some the Lippmann-Schwinger equation written in particular effective field theory. So they come up with a bunch of different interactions, models for interactions, try to constrain coefficients of these interactions from some data, and then using their knowledge from S-matrix theory, the fact that they know about these complex Riemann sheets, they continue the amplitude from the first Riemann sheet to the second Riemann sheet to find poles. This is essentially what you see here. You see some plots of real energy versus imaginary energy near the threshold, which I believe is defined at 0. And you see a bunch of dots, which means essentially that they probably used some statistical analysis. They constrained their data, their analytic model using some discrete set of points. Of course, this can be only done with certain precision. You use many different models and then average over them. You get all these poles, you average over pole positions, and that gives you the final pole position of the state that you are looking for. So just to show you that this is what's being done, it's these words that I'm teaching you are not completely useless. Okay, so that being said, let's me move on. Okay, so what I want to do today is, this is previous episode, this is today's episode. So I want to finish what we started talking about. I promised you during lecture 1 a lot of formal theorems. I realized very soon that there's no way I can show you any of that. So again, we'll continue with some simple analogies, simple models. And I'll just talk about angular dependence a little bit in this non-relativistic quantum mechanical example. And then we'll move on to talk about unitarity. Because I told you that unitarity is what really is a physical principle behind appearance of these cuts. And it's essentially the crown jewel in the S-matrix theory. But I just wanted to tell you that if you want more formal treatment, there's this excellent book, Scattering in Quantum Field Theories. So if you prefer rigorous math more than hand-waving, then I encourage you to check this out. And now let's talk about this angular dependence in this simple quantum mechanical model. So what we do, we consider Schrödinger equation, just like yesterday, but now we do not ignore the angular part, so there will be some theta dependence. So you know the Schrödinger equation can be in radial coordinates, can be split into radial part and angular part, and the solution to angular parts are essentially Legendre polynomials. So the scattering function that describes our incoming and outgoing state will essentially have some Legendre polynomial in front of it, and then we'll have to consider all different wave packets in the energy space. Now, if you consider higher angular momenta, so L is our angular momentum, the functions that stand here are the Hankel functions. I'll use P. Of course, P is related to E. It's a square root of E, or less, up to factors of 2 and mass. And then our scattering matrix will start depending on the angular momentum L. There will be another Hankel. And the time dependence. And there will be some dE here under a style. Probably the only important thing you need to know about Hankel functions is that they are complex conjugates of each other. So 2 is H1 star. And let us define, again, this is something that you were taught during the online part of the school. You can introduce the scattering amplitude. It will appear later today in the relativistic context again. You will see the same equation, slightly different form. And you remember that the scattering amplitude can be expressed in the terms of phase shift. So let me write that down. And maybe you'll see this equation today again. One over P here. Probably if you define here with P, maybe I'm wrong. Okay, but very good. And we can define, this FL is defined as partial wave projection. We'll again talk about this in the relativistic part of today's lecture, of the scattering amplitude that depends both on momentum or energy and the scattering angle. So it depends just on momentum, and it has this Legendre polynomials. Okay, so I told you, I finished our lecture yesterday by saying, well, you can consider this as a function, complex function, in one complex variable, momentum, at some fixed angle, or you can just study this partial F projected version, forgetting about the angular part. But you can also complexify the angle and ask the question, what happens when the angle is complex? So the main lesson that you learned from studying the simple square wave potential by using this solution and solving for the S matrix. I will not write you down the full solution. It's essentially a combination of these Hankel functions in the numerator and denominator such that the S matrix becomes a pure phase. But the main lesson is that for so-called ultra-local potentials, this F P theta is also analytic in angle. Or maybe I should write in this variable z, which is cosine theta. I want to talk about z because z will be a more natural variable when we start doing partial wave projections in the relativistic case. What do I mean by ultra-local potentials? I mean potentials that have, how do you say it? Compact support. So potentials that are zero outside of some finite open set in your space, position space. So things like bumps that have some well-defined range of interactions. This is an interesting lesson, maybe we should call it a theorem. And then the question is, how do you prove this theorem? And so I'm a very lazy lecturer. The hard part will be on you. Because honestly, I don't know how to do it. Maybe I know and I'm just lying. So let's consider so-called Cauchy-Hadamard theorem. Again, a little bit of complex analysis. So I say this is analytic in Z, but we wrote this function as an infinite series in angular momentum. L goes from 0 to infinity, of course. And there's a lot of theorems about complex functions defined as series. The theorems usually tell you how the coefficients in these expansions must behave for the series to be convergent and what are the analytic properties of the resulting sum. And Cauchy-Hadamard theorem essentially tells you that if you have some function of variable z and it's defined as some, essentially as a series expansion, if this a k coefficients behave like decay like some number r to some power k, then the function f of z is analytic in a circle or in a disk of radius a. Radius r, sorry. Now, if starting from some k, this convergence is faster, so if ak is smaller, so r to minus k, starting from some k, for k larger than some, let's call it k prime, then f of z is analytic everywhere. Okay, this is Cauchy-Hadamard theorem, very beautiful theorem. The question is, what does it have to do with expansion in Legendre polynomials? There is a corresponding theorem called Neumann theorem. That says almost exactly the same thing, but for functions that are defined as, let's use different name for coefficients, as expansion in Legendre polynomials. Essentially, you can prove a bunch of theorems of this type for functions that form some orthogonal basis in a space of functions. So Legendre polynomials are one of them. And essentially, all these statements hold with a slight difference that the convergence or analyticity is proven not in a disk of some radius, but in an ellipse. An ellipse with major and minor axes given by this expression. As far as I can remember, probably I don't remember. If this is correct, I would be surprised. So let me see. Almost correct. Again, I have two factors of 2. So now, I just told you there are some theorems that exist. How do we prove that this coefficient ck decay faster than r to minus k? For, let's say, not all ultralocal potentials, but for this spherical bump. And for simplicity, we will consider a hard sphere approximation. So essentially, it's impenetrable bump. The potential goes to infinity. It simplifies the expression for the S matrix. Of course, we need to think about F, which is related to S in this way. And F is given by this expression. So essentially, the problem is, and this will be your homework, to show, based on this expression, that this F else behaves something like this. And it's a highly non-trivial problem. I would say it's quite difficult. But if you can do it, please come to me and I'll give you a prize. My goodness. There are better things than cash, like handshake, smile. Okay, so this is a challenging problem for all of you. You seem to be extremely ambitious. So good luck with that. And I wouldn't be surprised if something like that appears at the exam on Friday. And you don't shake your head. Okay, how are we doing on time? As usually, very poorly. L. So essentially, the convergence is improved by this logarithm. L to the L. Already a hint. Okay, so this is ultralocal potentials. We know that these ultralocal potentials, although they might be a good approximation of nature in certain circumstances, I mean, basics of nuclear theory, if you read like classic textbook by Landau, were essentially rooted in study of the square well potential. But, well, probably something like Yukawa that describes exchanges of particles is more realistic. Yukawa potential is no longer an ultra-local potential because it doesn't have finite or compact support. It decays exponentially. So this is what I would call a local potential rather than ultra-local potential. So all potentials that decay exponentially for large distances will be called local potentials, and they have slightly different analytic properties. A lot of properties that we've learned on the simple models, CATs, analytic structure in the momentum plane still hold. So in the momentum plane, scattering amplitudes of Yukawa type will still be analytic up to certain number of poles that are bound state poles as usual. But more complicated structures can appear in the lower half plane, things like so-called anomalous thresholds or Landau singularities. So when I talk about this, and I'm talking in the context of angular dependence problems, we need to fix some variables when we discuss that. So momentum transfer will be considered fixed. And this is like fixing the Mandelstam T variable in relativistic case. And we will consider energy, which is, again, momentum, to be the variable of interest. Okay. And this is like Mandelstam S in the relativistic context. So I won't start proving or showing theorems or results for the Yukawa potential. Really the main difference or the main message that I want you to take away is that in this complex momentum plane, we'll have, as I said, bound states. We'll have virtual states, resonances, and then a bunch of complicated stuff here, branch CATs, branch point singularities that are called Landau singularities. Maybe, okay, this is something that you might want to look up later, so let me write it using large letters. So these are essentially singularities that come from analysis of perturbative behavior of Lippmann-Schwinger equation. You take your Lippmann-Schwinger equation, you expand it term by term. You see that each term, that there are higher order terms have certain integrals. In quantum field theory, you would call them loop integrals, with a bunch of denominators. And then whenever the particles that are described, intermediate particles that are described by these energy denominators, or propagators, you would call them, whenever they become physical, there will be some singularities generated in these integrals from certain very beautiful and definitely worth studying. I encourage you to study this. We will probably won't have time to do it, maybe during exercises, from so-called pinching or endpoint singularities. So there's a classification of the ways in which singularities in complex integrals can emerge. And those are some types of that. So those are Landau singularities. And again, singularities that appear, they have some physical meaning. As I said, this is when some exchange or intermediate particles in our loop diagrams go on shell in QFT sense or become physical, or some people say classical in quantum mechanical sense, which essentially means that they can propagate for a very long time. This is how I like to think about this. As singularities in the amplitudes emerge whenever something can propagate for a very long time. See, there are bound states that live infinitely long, and then by studying unitarity, we'll understand that branch cuts correspond to the possibility of some number of particles emerging from a scattering process and propagating for an infinitely long time because they don't violate energy conservation. They don't live for some small time due to uncertainty principle. They can just propagate forever because they are on a shell. Okay, so that's one important thing that I wanted to mention. And the other one, so this is what you learn by analyzing behavior of Lippmann-Schwinger equation, assuming momentum transfer is fixed and studying energy dependence, but you also can study the angular dependence and analyticity in angles, and that also leads to whole fields with their own names, things like Regge theory. Which is something that in this context you would use to prove that the scattering amplitude is analytic beyond sort of this ellipse that I would call it the basic ellipse. In the complex Z-plane. Of course, there's a lot more to Regge theory. Essentially, in this particular context, you can rewrite your partial wave expansion as an expression for an object that is an analytic continuation of this expansion in complex angular momentum. So we talk about E, cosine theta becoming complex. Now we are adding angular momentum to this set. And it's a beautiful theory that I would love to talk about more, but unfortunately we have to finally talk about relativistic scattering theory. So just if you're interested, read about Regge theory and what does it even mean to consider complex angular momenta. We know angular momenta are quantized, are integers. So what does it even mean? Okay. So finally, the topic of this lecture, relativistic scattering theory. What are the main differences compared to these non-relativistic cases that we discussed? Well, singularity structure of the amplitudes is very similar. However, we'll consider the singularity structure in ST and U variables rather than energy or cosine theta variables. And another difference is that there's crossing symmetry that relates these variables to each other. So it's not like cosine theta is entirely independent of energy, because crossing will relate singularities in one variable to singularities in another variable. This typically complicates certain things, also makes it exciting, and then in relativistic case, we can consider processes like particle-antiparticle production, essentially multi-particle, maybe that's the better way to write it, effects. That also can complicate the complex analysis of scattering amplitudes. This is something that I will talk on about Friday during my colloquium. And we'll discuss these two topics and unitarity of relativistic scattering amplitudes today and tomorrow. Okay, so the first revelation. For simplicity, we'll be considering scattering of identical particles of the same mass. You remember this relation from the exercise sessions. Probably some of you, when we were deriving it, I think when Bruna derived it, thought, oh my goodness, it's so trivial. What am I doing here? I'm too smart for that. No. Never underestimate simple formulas. This is a very important formula. Because it relates these three variables, these three Mandelstam variables to each other. And it will allow us to tell something about singularities of the scattering amplitude in these variables. And this was sort of one of the breakthroughs when people were thinking about S-matrix theory in the 50s or 60s due to Mandelstam, as far as I remember. Essentially, Mandelstam, he was a South African physicist. He came to the US. I think he was a PhD student or postdoc at Columbia, very unknown. And Chu, at the time, was a professor at Berkeley. He went to Washington, DC for some conference and noticed, oh, there's this guy in the conference, Mandelstam, who's talking about scattering amplitudes, so the same topic I'm working on, and he's the only other guy that talks about it, so I should approach him and see what he has to say. Maybe we can collaborate. So he approached, he went to Mandelstam's lecture, talk, and Mandelstam was talking about analyticity in angles, essentially claiming that functions, scattering amplitudes should not be just considered as analytic functions in energies, but also angles, or essentially these T and U variables. And Chu didn't understand anything from the lecture, although he was an expert on the topic, and thought, oh my goodness, this schoolboy, he has no idea what he's talking about. So ridiculous. I'll just politely ask him to come with me after his talk, and I'll teach him how this stuff is done. So, it's an anecdote that Chu told, so I trust him. So he took Mandelstam on a side, they sat down together, and Chu started asking questions to Mandelstam. Mandelstam started explaining his ideas, and Chu was, for the first hour, completely convinced this is rubbish, this guy has no idea what he's talking about. I don't understand anything you're talking about. But then, second, third hour went by, and Chu wasn't so sure anymore. He still didn't understand what Mandelstam was talking about, but he got an impression that Mandelstam knows what he's talking about. And he offered him a job at Berkeley. So this is how things were done those times. You go with a guy, talk to him, you have no idea what he's talking about, so you give him a job. And then they wrote a bunch of extremely important papers on this. No, unfortunately. Okay, so one of the crucial ideas that Mandelstam introduced, and I think I'll use the central part of the board, because I need a large chunk, is this idea of the Mandelstam plane. It's a beautiful geometric idea that's related to this simple but important equation. Essentially, if you know that this equation implies that you really need just two variables to describe scattering amplitudes. So if you want to study analytic properties of your amplitudes, you could say, write this as your complex t-axis, this as your complex s-axis, and study amplitude as a multivariable function in this plane. And Mandelstam came up with a beautiful picture. It's equilateral picture of complex energy plane that makes things very easy to explain. You draw an equilateral triangle, and you say that this line corresponds to s equal to 0. This line will correspond to t equals to 0. So that leaves us with that line, which will correspond to u equal to 0. And we measure distance from this line in the s direction like this, in the t direction here, in the u direction here. And then you can, since s, t, and u are constrained by this equation, you can uniquely define any point in this equilateral or Mandelstam plane just by having two of those variables, t, s, and u. And the sum of these lengths must always be equal to 4m squared. So this is an interesting way of seeing things, using three variables to describe a really two-dimensional plane. But you can do this because of this constraint, st plus u is 4m squared. So the sum of these distances from each of the lines is a constant. And then Mandelstam says, what are the physical values, or asks a question, what are the physical values of these variables? So let's think about the s variable. I'm using the notation from the exercises. So we have a scattering process. I hope it's consistent with what we did during the exercises. P1 and P2 are the incoming momenta. P3 and P4 are outgoing momenta. And we define T as momentum transfer, U as momentum transfer, and S as essentially square of total energy if you go to the center of mass frame. So, since this is energy in the total energy of mass frame squared, and we remember we express it in terms of momentum during exercises. Oh my goodness, this is bad handwriting. Okay. The physical value is when particles are at rest, center of mass frame. So there's no motion whatsoever. So this will be 4m squared, which is essentially what we will call production threshold energy, because this is how much energy you need, minimal energy, to produce two particles of mass m. Okay, so that's intuitive. And if you look at Mandelstam plot, this is this point. And everything above that is what Mandelstam would call the allowed physical region for the scattering to occur in the S channel. So imagine, for example, we consider something like a reaction pi naught with these two momenta going to pi plus pi minus with the outgoing momenta. So if this reaction lives here, it is physical. If we continue our Mandelstam variables here or here or here, it's no longer a physical reaction. Possibly, depending on the singularity structure of the amplitude, we can perform analytic continuation from this region to some other regions in this complex energy plane. And now Mandelstam says, well, we know there's a crossing symmetry. So one of the important differences between non-relativistic quantum mechanics. So we know that the amplitude that describes the process in this channel is the same as the amplitude that describes the following reaction. It's a reaction in which we switch one of the particles with one of the particles in the outgoing state for an antiparticle in the incoming state. That's what crossing symmetry is. With momenta reversed, I need to remember that. So this is P naught of P1, pi naught of P1, pi minus of minus P3, pi naught of minus P2, and pi minus of P4. So this amplitude that describes this process also describes this process. But this process has different kinematics, right? The S variable, so total energy squared for this process will be different because it's P1 minus P3, not P1 plus P2. And that's interesting because we can identify the S Mandelstam S variable for this process as a T variable from the previous old process that we started with. So let's call this A, let's call this process B. So we'll say that S, let's call it T for reasons that I'll explain later. Mandelstam variable for this new process that we consider using the power of crossing symmetry is described by a new set of variables. Oh, yes. Did I mess up? Maybe not. Okay, but we identify this as a T variable of the crossed or the original reaction, and this as the S variable of the original reaction. But this process is physical, just like in here, when we have enough energy to produce two particles. So this ST variable is larger than 4m squared, or in the language of old variables, old T is larger than 4m squared. So what Mandelstam says, in this plane, this process B is represented by the same amplitude, but if we take different region of in this plane, essentially. And again, this point, this is equilateral triangle, is 4m squared. And again, using crossing, we can switch the other two particles, and then we have P naught by 1 here, P plus minus P4, going to P naught P3, and P naught of minus P4. And you can convince yourself easily that the new S-channel variable will be P1 minus P4 squared. So this is our old U variable. And again, the scattering for this particular process becomes physical if this is larger than 4m squared. So it is described by this piece, or it becomes physical in this piece of the complex energy plane, or this Mandelstam plane. So what have we learned? We have learned that the scattering processes in this A, B, and C channel, which in the literature will be called the S channel, the T channel, and the U channel, which I didn't want to call them that at first. I prefer to call them A, B, and C, because people usually confuse S channel with S variable or U channel with U variable. These different processes can be considered, and they are described by the same amplitude, and as we discussed during the first lecture about crossing analyticity, we can consider the value of this amplitude in this complex and is in this part of the complex energy plane, an analytic continuation of the amplitude in this plane, and the amplitude in this part of the plane is an analytic continuation of the amplitude in this plane, and so on. And now, in axiomatic quantum field theory, in S-matrix theory, without making certain restrictive assumptions, I suppose, or actually, it is taken as an axiom. You assume that this analytic continuation can be performed. Just sorry? Less. Sorry, you are referring to one of these equations? Which one? This one. No, ST should be larger than 4m squared. For this process to be physical. Yes, but for this process to be physical, T must be less than 0. Right? Forget about crossing whatsoever. Assume we are just considering this particular process with variables, incoming and outgoing for momenta, for some unknown reason given by this strange choice. We use minus P3 in the incoming state and minus P2 in the outgoing state, for whatever reason. S variable is P1 minus P3. How this, no, these equations do not violate this formula. And which you can check if you just add this together. Since these are equal to the old variable st and u, sorry, u goes to u, the new variables added together will give you 4m squared, because the old variables added together gives you 4m squared. Has it resolved the confusion? Another question. Sorry? Oh yes, there's charge violation. So I say we publish it because we discovered charge violation. And this is a very inspiring school. Now, of course, there should be plus here. Yeah, sorry for writing in this direction. It's not probably very readable. Okay, I'm probably run out of time. Andrew is staring at me. No, I still have 3 minutes. So don't stare at me. What I was going to say. Okay, we will not talk about unitarity today, apparently. In the language of, or in the framework of axiomatic QFT, you can, starting from some minimal set of assumptions, like causality, for example, or this microcausality that I introduced at the end of the lecture yesterday. Also, assumptions about positivity of the spectrum, mass gap, etc. You can show that this analytic continuation between these different S, T, and U channel pieces of the Mandelstam plane is possible. It's not necessarily trivial because you have to avoid certain singularities. Okay, before I stop, let me just say 2 things. First one, appreciate this plot. Try to understand it. I mean, every little detail of this plot. It's a brilliant geometric idea. And notice that whenever you feel bad about yourself, remember that about 99.99 9% of the world population doesn't understand this plot, but you do. Doesn't mean that they are worse. I mean, my parents don't understand this plot. I still love them. Probably if they knew that I understand this plot, they wouldn't love me anymore, but that's a different tragedy. But yeah, that's my encouragement. Remember, this is a beautiful plot you need to understand. A second thing I wanted to say is that unitarity is esoteric property that I've been mentioning all this time and promised you to discuss today, and of course I ran out of time, so we'll discuss it tomorrow. Implies the presence of branch cut singularities in a complex energy plane, or in the relativistic case, in the complex S plane. But since there is, in a certain sense of crossing symmetry, no real difference between ST and U, there will be branch point singularities in T and U variables that also start at the production thresholds, where the opening for two-body scattering appears. So, if there is a cut in your scattering amplitude here, there will be a cut here, there will be a cut here. If you think about particular problem, you have your scattering amplitude described as a function of S and T variables, and you fix T. And you know that your scattering amplitude in the complex S plane has some branch cut singularity at some point. From this equation that I told you never to underestimate, let me take that here, you can see that at S equal 4m squared minus U minus T, so at T is a fixed parameter now. Since U will have a branch point singularity at 4m squared, for the same reason there is a branch point singularity in the S variable, which is unitarity, which we'll discuss later. There will be a branch point singularity in S variable starting at minus T, something that we call a cross-channel cut, or left-hand cut. So there will be additional singularities in your complex energy plane that also have physical meaning. They are imposed by crossing and are essentially a consequence of the forces in your system that are represented in, let's say, the Feynman diagrammatic language as particle exchanges. Okay, and this is where I guess need to stop today. Thank you.
All right, questions? We have one ready.
Thank you for the lecture. I wanted to ask about the S, T, and U channels that you mentioned.
Mm-hmm.
Normally in quantum field theory, you define the S, T, and U channels of a process, and they have always the same initial state and final state particles. But that's not the case here.
No, I mean, I don't understand. Why would they?
So,
if you consider identical particles, like in the phi to free theory, you probably think about ST and U diagrams. Then since the particles are identical, switching antiparticle for a particle in the final and initial state doesn't change anything. So for example, if I considered reaction like pi naught to pi naught, then switching antiparticle with particle doesn't mean anything because pion is its own antiparticle. So in this case, crossing would imply some permutation symmetry. So if you have a function that describes your process, crossing means changing incoming momentarily, but not changing particles. You could say that, I don't know, this function satisfies a relation like this. But in general, I think, for example, if you consider QED, crossing in QED, if you switch, if you have electron and anti-electron, you have to switch those in the incoming and outgoing state.
Yeah, I understand, but for example, if you consider electron-positron scattering, when you refer to the ST and U channels of electron-positron scattering, it's the same electron-positron to electron-positron scattering. And they
so
are
you're
called
talking about
ST
something
and U.
like Baba scattering?
Yeah.
No, Baba is E plus, right? To E plus.
I don't know.
Okay.
But
don't
if you
remember.
do E plus, E minus to E plus, E minus, you have the ST and U channels.
Yes.
But they all have the same initial and final state particles.
Yes.
And that's what we understand. That's what I understood for ST and U channel.
Okay. Let's not use ST and U because this might be confusing. Let's consider A, B, and C.
Okay.
What crossing says, crossing symmetry says, you can consider particles moving forward in time as antiparticles moving backwards in time. Okay? That's the statement of crossing symmetry. So indeed, you can apply it to E plus, E minus scattering QED. And then if you switch E plus for E minus in E plus in incoming state, it will become E minus in the outgoing state. You need to do another switch to have 2-to-2 scattering. And crossing does not, maybe I should...
okay.
Crossing does, so that's why you have the same initial and final states.
So it's just a coincidence.
Yes. By the way, crossing also allows for going from something like 2-to-2 state to 1-to-3 state, right? We can take a particle, switch it from antiparticle. And the question is, what's the region in the Mandelstam plane that corresponds to that? If it's kinematically allowed. So if we have a process, some particle A, B goes to CD, we can cross it, let's say, and do something like this. Of course, for this process to be physical, the mass of A must be larger than the sum of masses of products because it must decay, must have a phase space to decay. What's the region in the Mandelstam plane that corresponds to this crossed channel? Maybe that should go as the exam question. It's a tricky one. I'll give you the answer. It's here. So that completes this beautiful picture.
Any more questions? I don't see any. Feel free to ask after lecture anyway. And now we have the coffee break until 11:15, and then we will resume the lectures.